Okay, so there is a couple of different things I want to talk about today. And most of this has to do with, well, all of this has to do with the use of Laplace transforms in simplifying problems of differential equations. Okay, so before we move on, I'm going to sort of talk about something slightly different than what we introduced the last time, which was basically the step function. There is one problem from your tutorial, which I don't think I did enough justice to. And this is a fairly simple problem, but this again goes to show you the power of Laplace transforms. And this has to do with the idea of systems of equations, systems of ODEs, excuse me. Okay, so the idea is that given a system of two differential equations, you can actually solve for both using Laplace transforms. Now, I will not belabor this point, but we will just look at one particular example and see how this works in practice. Okay, so the example that we're going to do is y prime plus 2y plus z equals 0. Z prime minus y plus 2z equals 0. Okay. And the initial conditions are, well, this is a first order differential equation. So we just need one initial condition. And the initial condition is, I will choose to be y of 0 equals z of 0 equals 1. You could, of course, solve it for any other initial condition also, but this is fairly straightforward. Okay. So how would you do this? Well, you don't need Laplace transforms, you can argue, but the use of Laplace transforms, as usual, makes things quite easy. So take the Laplace transform on both these equations. So you get Laplace transform y prime plus 2y plus z equals 0. The Laplace transform of z prime minus y plus 2z equals 0, right? Now, Laplace transform being a linear operation, this is a sum of three terms in each of these equations, and use the fact that the Laplace transform of y prime is s times the Laplace transform of y minus y at 0. And the notation that we have is this, right? So put that in both these equations, and the first equation becomes an algebraic equation, which becomes s times y, capital Y, minus y of 0, and y of 0 for us is 1, right? Plus 2 times the Laplace transform of y plus the Laplace transform of z using the same notation. I will write this as a capital Z, and this is equal to 0, right? Excuse me. And the second equation becomes s times capital Z minus z at 0, which is also 1 for us, minus capital Y plus 2 times capital Z equals 0. Okay. Now this becomes simple because now what you have is two algebraic equations, and I can clean this up a little bit by writing the first equation as s plus 2 times the Laplace transform of little y plus the Laplace transform of little z equals 1, and minus the Laplace transform of y plus s plus 2 times the Laplace transform of z equals 1. These are the two equations, and I can go ahead and solve this, right? So if I multiply the first equation by, if I multiply the second equation by s plus 2 and add these two equations up, I will get 1 plus s plus 2 whole square times z equals s plus 2 plus 1, which is s plus 3. Okay. So this tells me that the Laplace transform of z, which is capital Z, is s plus 3 divided by s plus 2 the whole square plus 1, which is 1 square. Okay, and this is where your knowledge of Laplace transforms should come into the picture. How would you quickly understand what little z is? Well, I will write this as s plus 2 divided by plus 1 divided by s plus 2 square plus 1 square, right? So little z, which is given by the inverse Laplace transform of capital Z, is the inverse Laplace transform of s plus 2 divided by s plus 2 square plus 1 square plus the inverse Laplace transform of 1 over s plus 2 square plus 1 square. Can anyone quickly tell me what the Laplace transforms of these two functions are?
Cos t and sin t.
Cos t and sin t, but not exactly cos t and sin t, right? Because the s is shifted to s plus 2. So you can guess that there is an e to the at at play here, right? So the a here in this case turns out to be minus 2. So the first guy would be e to the minus 2t cosine t. And the second guy is, of course, e to the minus 2t sine t. So your little z turns out to be e to the minus 2t times cosine t plus sine t. That's right. Does everyone agree?
Yes, sir.
So you can figure out what capital Y is and then find the inverse Laplace transform of capital Y and figure the answer out. So the Laplace transform can also be used to solve systems of ODEs using this simple example. Okay. So there are cases where the Laplace transform helps in solving ODEs that can be solved by other means also. But there are also cases where the Laplace transform might be the only way to go about doing things, okay? Or if not the only way, at least the easiest way, because the other ways turn out to be rather complex. So we're going to go ahead and look at an example of such a class of problems. And this is the reason why we introduced this step function. So I want you to complete this problem. So homework, oops, excuse me. Complete this problem if you have not done so already. Okay. So now I will go ahead and switch gears and go back to our discussion of the step function, because I want to talk about something rather interesting. So if you go back to our step function definition, we introduced a function of this sort. Well, why did we introduce a function of this sort? I will explain that in a second. So basically the function that we introduced was called the step function, which was basically 1 if the argument t is greater than a or 0 before, okay? So there is no other value this function can take. And I told you, well, this seems like a weird thing to do, but it's very useful in problems which require switching on and switching off something. Okay, for example, an electrical impulse or something like that. So if you want to switch on and switch off something, the Heaviside step function is actually a remarkably compact way with which to model the system. Okay, so we also discussed that, well, there's two important things we discussed in this under this section. The first thing we discussed was how to calculate the Laplace transform of such a function, which was actually quite easy to do by direct integration. We found this was equal to e to the minus as over s. A more important thing was to understand what is called the second shifting theorem, which we call the t-shifting theorem. The content of this theorem is basically right here. Okay, so if you knew what the Laplace transform of a function f of t was, and let us say that is equal to f of capital F of s, then you could guess the Laplace transform of f of t minus a times ut minus a, and this is simply equal to e to the minus as times the Laplace transform of f. Now, this seems a little more complicated than the usual S shifting theorem that you saw, which was basically shifting the argument of the integral, which was, well, shifting the exponent in the e to the minus as, which was fairly straightforward to understand. So the question is, why do you have to understand this t-shifting theorem, and how does it actually come into the picture in a practical case? So we will solve a problem again as an example problem to illustrate a how to model an impulse using the Heaviside step function, and B, to understand how Laplace transform comes into the picture and makes life easy for us. Okay. So this is actually an example problem from your textbook, which is actually a very nice example problem. So we are going to look at a driven damped harmonic oscillator. But the driving force, up till now, we have looked at driving forces that are harmonic functions like cosine omega t to the I omega t and things like that, or exponential functions. But now we're going to look at something like a square wave impulse. Okay. So the example that we're going to look at is a mass spring driven damped simple harmonic oscillator under a square wave impulse, a square wave driving force. Okay. So the equation for a driven simple harmonic oscillator is y double prime plus cy prime plus ky equals r of t. C is the damping constant, K is the spring constant, and R is the driving force. Okay. So we'll take a very specific example, y double prime plus 3y prime plus 2y equals R of t. And my initial conditions, because I'm treating this as an initial value problem, and this is a second order differential equation, I need two constants. I'll simply choose at time t equal to 0, these guys are both 0. The position and velocity of the object is both 0. Okay. Now, R of t is a square wave. Okay, what does this mean? So, you know, you guys are engineers, so you know exactly how to write a square wave, how to draw a square wave. So this looks something like this. Okay. So this is t equals 1, this is t equals 2, and this is of unit height. This is a square wave impulse. So I am driving the simple harmonic oscillator with a square wave impulse. Okay. Now, what does this mean, and what is the mathematical form for R of t in this case? And how do I solve this differential equation? Well, it turns out that I can model this square wave using the Heaviside step function. And that is why the step function is practically useful in applications that involve switching on and switching off. So here I'm switching on and switching off. So the square wave impulse doesn't extend to the left of t equals 1 and to the right of t equals 2. So you can sort of understand how to use a step function in this case. Well, if I simply model this as u of t minus 1, what is u of t minus 1? Well, u of t minus 1 equals 0 if t is less than 1 and 1 if t is greater than 1. So I want this function to be 1 for t greater than 1, but I don't want it to be 1 for all t greater than 1. I just want it to be 1 for t equals 1 to t equals 2, nothing more. If I model this, so this u of t minus 1 itself doesn't work, because u of t minus 1 is basically this guy. Sorry, so I will write both and then write them on below each other. Similarly, if I model this as u of t minus 2, this is equal to 0 if t is less than 2 and 1 if t is greater than 2. Okay. So I cannot model this as either u of t minus 1 or u of t minus 2, because u of t minus 1 would be this, right, at t equals 1. And u of t minus 2 would be this, okay, at t equals 2. But all I want is this right here. The way I will do this is by marrying these two step functions in a linear form. So suppose if I construct something like u of So let me call this R of t because I know this is the answer, but I will explain why this is the answer. U of t minus 1 minus U of t minus 2. Okay. What does this mean? Well, let us investigate what this function is for all values of t. Well, for t less than 1, R of t would be, well, for t less than 1, U of t minus 1 is obviously 0. U of t minus 2 is also obviously 0 because for all t less than 2, U of t minus 2 is 0. So anything less than 1 is obviously less than 2. So this is 0. And this is perfectly okay because for t less than 1, I want it to be 0. Now what happens for t greater than 2? For t greater than 2, U of t minus 1 is 1 because U of t minus 1 is 1 for any t greater than 1. So 2 is certainly greater than 1. So R of t in this case would be 1. And U of t minus 2 is also 1 because for t greater than 2, U of t minus 2 is also 1. So 1 minus 1, this is 0. These two guys completely cancel each other. So for t greater than 2, this function is 0. Okay, so this is all. So this we have been able to reproduce this region and this region. How about the middle region? So in this region, t is greater than 1, which means U of t minus 1 is certainly 1. But U of t minus 2 is 0 because t is still less than 2. If as long as t is less than 2, U of t minus 2 is 0. So this is equal to 1. So this is also reproduced correctly. So by constructing this particular linear combination of step functions, you can actually talk about functions that are turned on and turned off in this particular fashion. Okay. Now suppose if you had a square wave impulse that repeated itself like this. Okay. You could still write this as a series of step functions. So that'll be your homework. So try and model this square wave impulse as a, I'll actually make this more precise because these are important kinds of problems that can be important at times. So suppose if you had a square wave impulse like this. That sort of kept repeating or stopped after 3 or whatever it is. Okay. So this is t equals 1, 2, 3, 4, 5, 6. So try and model this. So homework. Model this function using step functions. So the point is that if you had driving forces of this form, input to physical systems of this form, the step function is a convenient way to characterize these guys. So my initial ordinary differential equation that describes this driven harmonic oscillator can be written as y double prime plus 3y prime plus 2y equals R of t, which is U of t minus 1 minus U of t minus 2. And this might be difficult to do using your conventional knowledge of undetermined coefficients or other things because you do not really know how to go about doing this for inputs of this form. But using Laplace transform techniques, it becomes very simple. How so? Well, just approach it like you usually approach ODEs with the Laplace transforms. Take the Laplace transform on both sides. And remember that our initial conditions are y at 0, y prime at 0 are both 0. So this becomes, if I take the Laplace transform, y double prime plus 2y equals the Laplace transform of the step function at 1 minus the step function at 2. So this is s squared times capital Y plus 3 times capital S plus 2 times y, because y of 0, y prime of 0 are both equal to 0. So those factors don't come in. This is equal to, well, what is the Laplace transform of u of t minus 1? Remember that we just said that L of ut minus a is e to the minus as over s. So this is e to the, well, in this case, a is 1. So this is e to the minus s over s. And the second case, a is 2. So this is e to the minus 2s over s. And now this becomes again an algebraic equation that I can easily invert to find capital Y. Capital Y would be 1 divided by s times s square plus 3 plus 2 e to the minus s minus e to the minus 2s. Now, I'm guessing all of you know what partial fractions are. If you don't, please stop me. And you can write this guy as a series of partial fractions. You basically write this as, so this is basically 1 over s times s plus 1 times s plus 2, right? So you can write this as a over s plus b over s plus 1 plus c over s plus 2. Okay, and write this as a series of easier fractions to deal with. And if you do this, you can write this capital Y as e to the minus s minus e to the minus 2s times the quantity 1 over 2s minus 1 over s plus 1 plus 1 over 2s plus 2. Okay, so I leave this to you to check that this indeed reproduces this function. Okay, all right. So where does this leave us? Well, if I took the inverse Laplace transform on both sides, I'm golden. I know the answer. Y of t is the inverse Laplace transform of all of these guys. But this has factors of e to the minus s multiplying 1 over s and 1 over s plus 1. And this is where the t shifting comes into picture. So t shifting theorem tells us that the Laplace transform of f of t u of t minus a is basically e to the minus as times the Laplace transform of the function. Which means if I took the inverse Laplace transform of, so let us approach this in steps. So let me just look at the square bracket. The square bracket, which I will call capital F of some function, right? Because I'm going to use the t shifting theorem. So this is the exponential that multiplies this. This is this guy. Okay, so I'm after f of t first. Once I find f of t, I can figure out the solution to this in a straightforward fashion. So this is 1 over 2s minus 1 over s plus 1 plus 1 over 2 s plus 2. What would be the inverse Laplace transform of this? What is f of t?
So it will be half. It will be half half minus
Good, go ahead.
half minus e raised to minus t plus half into e raised to minus 2t.
Very good. So the idea that he was talking about basically is that the Laplace transform of a constant is 1 over s, right? So if the Laplace transform of a constant is 1 over s, the first guy is just half times 1. The constant meaning constant equals 1. So the first guy is just half times 1. The Laplace transform of 1 is 1 over s. So the first guy is easy to guess. F of t for the first one is just 1/2. For the second one, it is again of the form 1 over s, but the s is shifted by an amount plus 1. So a is minus 1 in this case. So this is e to the minus t. The second guy is again just 1 over s. In this case, a is of course minus 2. So we have, okay. So there it is. You have gotten the f of t. But now how do you find the solution to your original problem? The original problem was not calculating the Laplace transform of just this guy. It was calculating the Laplace transform of this multiplied by e to the minus s minus e to the minus 2s. But that is okay because y is L inverse of e to the minus s f of s. And the second part is L inverse e to the minus 2s f of s, right? Because the inverse Laplace transform is also a linear function. So I can piece this up into two different things. And in each of this, I will use the t shifting theorem. Basically, I am after the inverse Laplace transform of this guy, right? if the inverse Laplace transform of this guy is basically f of t times u of t minus a. So in the first case, a turns out to be 1. Sorry, this is not y, this is little y. So in the first case, a turns out to be 1. So this is basically f of t minus 1, u of t minus 1. And in the second case, a turns out to be 2. So this is f t minus 2, u t minus 2. So this is how the driven oscillator responds under a square wave impulse. So it will be good to understand what this function exactly is. So we know what f of t is, right? So let us look at this for different time regimes. The first part doesn't exist for t less than 1. The second part also doesn't exist for t less than 1, right? So y of t is such that for t less than 1, this is manifestly equal to 0. Now let us look at what this function is between t equals 1 and t equals 2. For t greater than 1 but less than 2, the second part doesn't contribute because u is t minus 2 and t is still less than 2, but the first part contributes. So what is f of t minus 1? This is 1/2 minus e to the minus t is t minus 1 now plus e to the minus 2 t minus 1. Okay, so I'll write everything in a nice form. So this is t less than 1. This is t between 1 and 2. And what happens if t is greater than 2? If t is greater than 2, of course, both of these guys contribute, right? So this will be 1/2 e to the minus this guy for t minus t equals t minus 2, and the same thing for t equals t minus 2. So putting everything together, you will get minus e minus of t minus 1 plus 1/2 e to the minus 2 t minus 1. That will be the first term. Minus of minus, which is plus e to the minus t minus 2 minus 1/2 e to the minus 2 t minus 2. So this will be for t greater than 2. This will be the response of the oscillator for this particular impulse. So notice that all of these are such that for very large times, the response vanishes, right? This is reminiscent of the fact that the square wave impulse is only acting for a short amount of time. From t equals 1 to t equals 2, basically. It is not there for a long time. Okay. So this is how you solve problems using Laplace transforms in the case of applications that are turned on and turned off. Does this make sense? Are there any questions about this? Any questions, any comments? Okay. So the next question that we want to ask is, okay, so we have understood that Laplace transforms are useful for cases in which you turn on and turn off things after a finite amount of time. But is it useful for problems in which you turn on and turn off things very, very fast? So in other words, let us say that I don't wait till t equals 2 to turn off this square wave. I wait for, let us say, 1 nanosecond or something like that. So instead of a broad pulse, suppose if I have a very, very short, very sharply peaked pulse, how will I deal with such a situation? So first, again, we'll proceed in steps. We'll first understand how to model this particular function. And then once we learn how to model it, we will understand how to solve this problem using Laplace transform techniques. Okay. So the question is, what happens if your pulse is very, very short? So short impulses. Okay. So this is basically a way of introducing what is called the Dirac delta function, which I no doubt you have already came across in your physics course. So Dirac actually had need for these functions for a very different reason. He wanted to understand how to deal with what are called infinite dimensional linear vector spaces called function spaces And he wanted a consistent way of defining these function spaces, and he invented this particular function. But this is strictly not a function in the true sense. Okay, so a function is supposed to be continuous. It is supposed to be following all these nice rules, but this guy breaks all these rules. Okay, so mathematicians would call this some kind of a distribution, but we will not make such distinctions, and we will simply call this functions, even though it is strictly not a function in that sense. Okay, so a Dirac delta function is basically used to model those physical and engineering systems in which the input or the driving force or whatever it is only acts for a very, very short amount of time. Okay, so it's a very, very sharply peaked function. So how do you model this peaked function? Suppose if you the same driven harmonic oscillator, suppose if I drive it, but with just a pulse at t equals 1 instead of a pulse that goes from t equals 1 to t equals 2. So I can look at the same problem, but with a very, very sharp pulse at t equals 1. So how would I model the system, and how would I solve the resulting differential equation? This is what we will try to understand now. So first, let us try to model this. Suppose if you consider a function fk, let us go by our pulse notation for now, and then we will make this pulse smaller and smaller and more sharply peaked. So consider fk of t minus a. This function is equal to 1 over k for a very short amount of time and 0 otherwise. In other words, what I'm trying to do is basically write this as this. So this is my t axis, and this is my f of t, and all I'm saying is that, let us say this is, this is t equals a, and this is t equals a plus k. Okay, and this pulse only exists for this amount of time, and the height of this pulse is 1 over k. Okay, so this is a rectangular pulse that exists only for a short amount of time interval. Time interval is equal to k, and the height of this guy is carefully chosen to be 1 over k. Now, the time interval of k is understandable. In some sense, I want to take the time interval closer and closer to just 1 point, so which means that I have to take k closer and closer to 0. Why did I choose the height to be 1 over k? Well, conventionally, this function is normalized so that the area of this pulse is 1. So the area of this pulse, area under this pulse rather, is the width of this pulse, which is k, times the height of this pulse, which is 1 over k. So this is just 1. So I'm choosing the height of this pulse to be 1 over k. Now, what happens if I take k to go to 0? The more correct way in which you can actually do this is, you know that area of a function is basically the integral, right? So area under the curve is 0 to infinity f of t minus a dt, right? But f of t minus a is 0 for every value of t, unless the t is between a and a plus k. So this is basically a plus k. And in this interval, the function is just a constant. And if you put this in, you will get 1. Excuse me. So the area under this curve is unity. Okay. Now, what happens if I keep squeezing this pulse? In other words, what happens if I keep taking k closer and closer to 0? So I define this pulse at just as much as possible at 1 instant of time rather than an interval of time. So if I keep squeezing this pulse, k going closer and closer to 0, well, I keep decreasing this width of the pulse. But since the height of the pulse is 1 over k, as I take k to 0, When I am squeezing the pulse, I'm decreasing the width, but increasing the height correspondingly. So as I keep doing this squeezing process, as I keep decreasing the width more and more, I'm increasing the height more and more, my pulse goes from, so looking like this, for example, excuse me. It was like this, right? Now it becomes like this. Now it becomes like this, right? Then it becomes an even taller building. So in the limit that I take k very, very close to 0, I get an infinitely tall impulse whose area under the curve is still unity, because I am shrinking it and increasing its height at the exact same rate. So the area under this curve is always going to be 1, and in the limit that I take k to 0, I'm going to get what is called limit k tends to 0 of this function is what is called the Dirac delta function. So the delta function itself is not a function, but it can be understood as the limit of some other function. Okay. And this is not the only function whose limit is a delta function. There's tons of other functions you can write down. For example, a Gaussian. You take a Gaussian and you keep squeezing the Gaussian, and then the Gaussian is going to become a narrower and narrower peak, which in the limit is going to look like a delta function. So there are many ways in which you can understand this as a limit of certain other functions. Okay. So the formal way to write down what a delta function is t minus a equals an infinitely high peak at t equals a and 0 otherwise. Okay. So since by construction we have constructed it such that the area under this curve is always unity, delta t minus a dt is normalized to 1. Okay. Now I'm guessing this is something you learned in your physics course, but what happens if you multiply some other function with the delta function? Well, if I take some function g of t and multiply it with delta t minus a, as it stands, this is not very meaningful, even though I can sort of understand this, because I can sort of understand this roughly as saying that, well, the delta function is infinity at t equals a, so this is going to blow up. But at every other instant of time t, this is basically 0. So this is going to give me 0. So I can make this more precise by defining this under an integral sign. Because under an integral sign, the delta function is well behaved, right? It is normalized to 1. So basically, this is going to be, the integration is going to be such that at every value of t not equal to a, you're going to get 0. At that particular value of t, you're going to pick out the value of g at that particular value of t, because that is the only point in which the delta function is non-zero. So this is going to pick out the value of the function g at t equals a. Okay. To give you a rough analogy, this is basically projecting out vectors, right? So for example, if you think of side, so if you write a vector as, let us say, vxi plus vyj, right? And so let us take a very specific example. So 2i plus 3j. Okay. And if I ask you what is the x component of this vector, you say it is 2. What is the y component of this vector? You say it is equal to 3. And if I ask you, how is it that you knew? You would simply laugh at me, because this is the number that multiplies I, and that is the number that multiplies j. But you actually had to do a mathematical operation to get this answer. And the mathematical operation is called the dot product, right? So when you typically ask what is the x component of this vector, you basically project out the x component by taking the dot product of this vector with I. So I dot I is 1, j dot I is 0. So this gives you 2. Right? So the dot product projects out that component of the vector that you're interested in. Similarly, the delta function is some kind of a projection. It's typically not, but it projects out the value of the function at that particular point t equals a. Okay, so it is serving the same purpose, but in the case of what is called an infinite dimensional vector space or something like that. Okay, so I think this is the language with which you studied delta functions in your physics course. So I wanted to make this connection. So it projects out the value of functions at specific points of space or time, whatever your variable is. Okay, so this could be x also. So for example, I can define delta function in the space domain. So integral, excuse me, integral even minus infinity to infinity, g of x delta of x minus a dx would be g of a. Okay, so on and so forth. The question is, what is the Laplace transform of the delta function? If I knew what the Laplace transform of the delta function is, I can go ahead and start doing something meaningful with it. So what is the Laplace transform of the delta function? If I knew the answer to this, then I can go ahead and solve the same problem that I solved. Instead of a square wave, I'll take a delta function impulse at precisely the point t equals 1 or t equals 5 or whatever it is. Okay, so how would I do this? Well, the way to do this is to take the same function that we looked at initially to model the square wave so that we kept squeezing the square wave, take the Laplace transform of that function, and then take the limit k goes to 0. So by now, you know how to model a square wave using the step functions. So fk of t minus a, right, which was basically 1 over k for t less than a. Sorry. So f of t minus a, which we wrote down as 1 over k for t between a and a plus k. So like this, 0 otherwise. Okay. The exact same way as we model the square wave, I can model this function as 1 over k u t minus a minus u of t minus a plus k. Okay. Why does this make sense? Well, for t less than a, both these functions vanish. So this is fine. For t greater than a plus k, these are both equal to 1. So 1 minus 1 is 0. That is also fine. Between a and a plus k, the second function is 0. The first function is 1. So this gives me 1 over k. So this correctly reproduces this particular function. So I can model this function as this particular combination of step functions. Okay, so if anybody has any questions about this, please do ask. Now I can always take the Laplace transform of this guy because I know what the Laplace transform of u is. So L of fk of t minus a, k is just a constant, so this is L of u t minus a minus L t minus a plus k. Okay. Again, use the factor, the Laplace transform of the Heaviside function is just e to the minus as over s. So this becomes 1 over ks times e to the minus as minus e to the minus a plus k times s. So this is the Laplace transform of the function f that we started with. But to get to the Dirac delta function, we took the limit k goes to 0, which means the Laplace transform of the delta function. So limit k goes to 0 of L of fkt minus a, which is basically the Laplace transform of the delta function, equals limit k goes to 0 of e to the minus as minus e to the minus a plus k times s divided by ks. Okay. How do you take the limit of this? Well, if I simply put k equal to 0, I get 0 over 0. So that is not very useful. So you take the L'Hopital formula, you differentiate the numerator, and the denominator with respect to k. So this is limit k goes to 0. If I differentiate the numerator, the e to the minus as is a constant as far as k is concerned. So this gives me so I can write this as e to the minus as times 1 minus e to the minus ks over ks. This is limit k goes to 0, excuse me, e to the minus as. If I differentiate the numerator with respect to k, mind you, I get s e to the minus ks, and the denominator is of course just s. Okay. Now the k goes to 0 limit is sensible, and this simply gives me e to the minus as. So the Laplace transform of the Dirac delta function is just e to the minus as. Okay. So we will, I will let you digest all this stuff today, and then in the next lecture, we will take this up again and then solve this exact same differential equation, but with the Dirac function driving force. Okay. So I'll stop here for today, and if you have any questions, you can ask me.